screws won't even.
But let's see if I can.
Is there like a B cable?
Oh, yeah, that's fine.
You are all right. Just don't touch it.
Yeah.
Oh, hi, Mazzaro. Nice to meet you.
Welcome.
Hi, nice to meet you.
Okay, so how about you put this on? We will first do the round of introduction and so on.
Oh, right.
So these are the used batteries?
Yes.
Or are these
No, these are the new ones.
Okay, then we should remember that these are
Just
the
check
new
what the power area is.
That is fine, I think it's full.
No one has ever been more wired up than this, right? Extra mic. Two
yeah.
different sound feeds.
Well, this is a very important talk.
It's a very important talk, clearly. You better live up to it.
3 hours long, very
3 hours.
detailed. That's what you want?
No problem, you know. You need to stop by 3, I guess. So 4 hours you can have. We'll go around the room and introduce people first. Yes, it will cost you a little bit of time, but this you can. Right, are we here? How do you know? Okay, so let's kick off the second week. I'll start with Steve, but in a minute. I don't have any real announcements, but as we did last week, we're going to go around the room for people to tell each other who they are, because not everyone knows everybody else. So I think that's a good idea. There's one change to the program that you've been given for practical reasons to do with travel. Ken Namoto will speak on Friday rather than today, and Ken Takuchi will speak today. Unless that's a surprise to you, in which case I'll have to change it back. So that was just what we arranged last week. You should have all the details, I guess, from Janine on wireless and stuff like that. So if you have any questions, you can just talk to one of us. This organizers me. I'm Niels. There's Sanjay, Luciano, and Sukant over there. Okay. So let's kick it off by going around the room. I'm Niels Anderson. I'm in Southampton. I do neutron star astrophysics, focusing mostly on things like superfluids and composition and things like that, and maybe seismology, a little bit like that.
Okay, so I'm Luciano Ortola. I am in Frankfurt. I'm interested in hydrodynamics and neutron stars, astrophysics of neutron stars. I do a lot of numerical relativity to get gravitational waveforms and counterparts.
I'm Jim Latimer from Stony Brook. I'm interested in the equation of state and how we can determine that from neutron stars and from nuclear physics.
I'm Gilly Mandel from the University of Birmingham. I'm a member of LIGO. I work on gravitational wave astrophysics, and particularly the interpretation of future observations in order to extract stellar and binary evolution.
I'm François Foucault, currently at CETA. I do numerical relativity, mostly black hole neutron star mergers.
Hi, I'm Kyriaki Dionysopoulos. I'm currently at Southampton. I'm mostly interested in general relativistic resistive magnetohydrodynamics, and in particular binary neutron star mergers and electromagnetic counterparts.
Hi, I'm Pablo Cerradura. I'm from the University of Valencia. I'm basically interested in hydrodynamics, in general relativity. I'm doing simulations on corpora supernovae and also on neutron stars in magnetars.
Hi, I'm Satya Prakash from Cardiff University in the UK. Interested in gravitational astronomy, observing gravitational waves on various different binaries and other systems.
So I'm Masaru Shibata from Kyoto University, and I'm working in numerical relativity, in particular in larger binary neutron star and black hole neutron star binaries.
I'm Sanjay Reddy. I'm a local here at the INT. My interests are in nuclear and neutrino physics. I'm particularly interested in extracting observational signatures of phases of dense matter inside neutron stars.
Hi, my name is Ken Takuchi from Yukawa Institute of Theoretical, and I'm interested in the binary neutron star situation in the very massive.
I'm Zachariah Etienne.
I'm a numerical relativist. I'll be starting as faculty at WVU, West Virginia University, in a couple of weeks. I spent the past year retooling and improving techniques in numerical relativity, getting ready to establish my research program, basically.
I'm Sukan Bose. I split my time between Washington State University in Pullman and the Interim University Center for Astronomy and Astrophysics in Pune, India. I'm also a member of the LIGO Scientific Collaboration. I primarily work on data analysis for detecting gravitational waves from compact binary coalescences.
I'm Wade Haxton from UC Berkeley. I'm primarily interested in neutrino physics and neutrino astrophysics, supernova, core collapse, and neutron star cooling.
I'm David Nielsen from Brigham Young University, and I am interested in numerical relativity and studying neutron star binaries, local neutron star binaries, and the electromagnetic counterparts.
At University of Wisconsin-Milwaukee. I'm mostly working on numerical relativity, in particular for black hole neutron stars, to derive accurate gravitational waves and predict electromagnetic counterparts.
Hi, I'm Rafael. I'm a student here at the INT, and I'm interested in the neutrino physics and core supernova.
Hi, I'm David Radice. I'm from Caltech. I do mostly numerical relativity of neutron star mergers, but I'm more in general also interested in numerical methods for relativistic hydrodynamics and radiation hydrodynamics.
Pablo Laguna, Georgia Tech, interested in numerical relativity and complex object merger.
I am Bhuvana Mukherjee. I am a postdoc in INT, Pune, India. Earlier I did mostly X-ray astronomy in time series analysis, and recently I am going into the gravitational wave sector, continuous gravitational wave in particular, and also binary neutron star method, and its electromagnetics.
Hi, I'm Navita Majumdar. I'm currently working at the Washington State University. I'm mainly interested in gravitational wave data analysis. I am working actually the detection problems, and it's for the binary black hole system and neutron star black hole system.
Hi, I'm Chris Messenger. I'm at the University of Glasgow. I'm interested in gravitational wave data analysis with compact binary coalescences, and specifically maybe using neutron star, gravitational wave neutron star detections for cosmology in the future.
I'm Mike Heraclius. I'm from Penn State. I'm an observational astronomer. I observe in optical and X-rays and many other bands. I'm interested in a lot of things. I happen to be a sabbatical visitor for these few months in the astronomy department, and I come here to listen to the talks. My interests most relevant to this workshop are the evolution of neutron stars in binary systems, high-mass X-ray binaries, which are the progenitors of binary neutron stars. I'm also interested in general in the astrophysics of sources of gravitation.
Excellent. So we shouldn't forget today's speaker. Who are you?
Oh, So I'm Steve Liebling from Long Island University, interested in numerical relativity. In particular, I'll talk about binary neutron star mergers today.
Okay, excellent. So I think having gone around the room, it's clear that last week we talked about convergence of the post-Newtonian expansion. This week, I think there's going to be some kind of different convergence, like higher order numerical convergence. So there you go. That's going to be the theme. Please don't make that the theme. Okay. That's it. Steve, over to you.
Okay, so nowhere else on my slide do I mention these collaborators, so I should get this out here right now. Plus, there have been some questions. I should also say, things were pretty informal last week. We've got new people and everything, but, I'm expecting lots of interruptions and arguments and all that stuff. So if you see anything you want to argue with, just, speak up. For those who want to know, Long Island University is just outside Queens on Long Island University, just Long Island, right? It's hard not to throw university on there. Okay, so I was told to sort of just give a kind of a status talk, kind of high level, not lots of details. We'll see how well I mean, looking back after writing the talk, it's not clear that too many people could understand a lot of the stuff on here, which is, I just sort of mentioned these things without going into them. So we'll see how that goes. So, just ask questions. If I can't answer it, maybe someone in the audience can. And yeah, I should say, a lot of the work I'm going to be talking about or mentioning, it has been done by people in the room. Okay, so here's just kind of a list. I'm not going to talk about all this, but what it takes to evolve a binary neutron star. So you need appropriate initial data. I should also say, towards the end of the talk, I'll talk about what I've done. So in particular, you can't see the outline for the talk at the top. I'm going to talk about some work we've done with electromagnetics with binary neutron stars and with neutrino cooling in binary neutron stars. So, sort of as we go, I'll mention a little bit about what we do. There are other solvers for initial data. We use this thing called Lorraine, which is produced in France. It's open source code, so lots of people use it. Gravity. So, in the olden days, we would talk forever about this stuff. It was not terribly exciting. It wasn't a lot of physics, so I don't want to say too much here. But I guess the fact that I can completely gloss over it is a real testament to the work of a lot of people that have gotten this stuff done. And I should also say that, there's going to be some talks this week that will talk about some of this stuff in more detail. In particular, I think Zach's going to talk about some improvements here. I suppose not too much. There was some discussion last week about accuracy. I'll have a slide about some errors and stuff. But in particular, boundary conditions are a big factor there, especially for the long runs that were being talked about last week. And then we've got the fluid methods, right? So we've got, this field kind of started with simple polytropes, then we go to ideal fluid. Now we're doing tabulated realistic equations of state. And still Niels isn't happy. He wants more. So, what comes after this, we'll have to see.
Happiness is greed.
Okay, yeah. But it's just, yeah, right. We always want more. And so another thing, I sort of want to mention for the non-numerical relativity types is that, we have a lot of this, but it takes some babysitting. The issues come up and stuff like that. It's not just a matter of, just starting up the code and see what happens. There's computational infrastructure. I'll mention just a little bit about that. Here's some stuff where we could certainly use some help. Extracting, signals, extracting the physics out of it, right? That's sort of the most important thing. Last week we talked about the gravitational wave signal. That's pretty well understood. I don't think people are complaining about, how we're extracting that. Though, it's not totally clear to me that some of this stuff isn't affecting this in a way that's not necessarily being accounted for. I'll talk about electromagnetics. In particular, we're getting the pointing flux out, which seems a poor proxy for what's actually going on. But what we do about that, I think, that's something we could discuss this week. And then there's the neutrinos, phototransport, some of that stuff. Photon. Okay, so last week numerical relativity came up a bit, and we talked about extracting information about the neutron star and the neutron star equation of state from the gravitational wave details. Much of this was pre-merger, some of it was post-merger. So I'm not going to talk too much about that. But for those who weren't here last week, you may want to just bring up those talks. They're online. And then we've got EM bursts, so short gamma ray bursts, and kilonova. I wasn't going to explain what those two things are, in part because I don't know a lot about the kilonovae. There are probably people here that know a lot more about the short gamma ray bursts. But to the extent that we can have anything to say from numerical relativity on those, that's a pretty exciting prospect. That's fun. So in particular, some questions are how much material is going to get ejected from a binary neutron star merger. So you're starting to see some papers on that. Whether an accretion disk forms, how much mass is in there that can potentially power a big burst, how long it lives, how long that corresponds to the gamma ray burst. And then, this is a huge thing. Can you get collimation? Can you get high Lorentz factors? So there are papers that talk about some of this stuff. It's not clear to me that there's a strong consensus that we've done much with that. And then the nuclear physics. So this is something I'm new to, but want to learn more. Lots of people, there's going to be a whole week at the end of this program on the R process. And again with ejecta and the composition of it. This, I'll talk about some of the work we've done here, but sort of the general idea of multi-messenger astronomy, I suppose maybe there are two main aspects to it. One is triggering. So you see something in optical or radio, and then you direct the LIGO people or the Virgo people to go look for a gravitational wave signal, or vice versa. You see something in LIGO, and miraculously you narrow it down to fewer than 100 square degrees, maybe. Or you have some kind of electromagnetic telescope with a wide field of view that can potentially find something. So I guess, I don't want to sound too negative about this prospect, but presumably it's only going to get better, and it's got a long ways to go. So that's, in some sense, that's a good thing. Instead of triggering, though, there's concurrent, or the possibility of concurrent detection. And if you do that, the potential for science extraction is really high, right? So to me, this is perhaps the most exciting thing possible, is that LIGO sees something, Swift sees something, IceCube sees something, and there's a talk by Ido Berger about some gamma ray burst, and he said it was just so cool to write a paper in a day about that. That would be pretty cool. Yeah.
Steve, you said you weren't going to say much about the kilonova, but I had a question that I was wondering whether numerical simulations are in a position to answer, because we had a workshop in Aspen on ultra-complex binaries just literally over the last couple of weeks, and there was a long discussion of kilonova there, and it seems that the people doing kilonova modeling, their main source of uncertainty is that they are not actually sure what is driving the ejecta, whether you have dynamical ejecta, whether these are neutrino-driven winds or these are viscous-driven winds, and the time scales and the velocities for the ejecta make a very big impact on the kind of signature you might expect to see, both on the details of the R process, nuclear synthesis, and the signatures you might expect to see afterwards. And I was wondering whether this is something that numerical relativity simulations might begin to approach being able to answer.
I mean, I don't know if anyone else wants to say anything, but my first response is that the ejecta is very tough right now just to get any kind of accuracy with respect to the ejecta. But answering the types of questions that you're asking, I think the time scales are going to be a lot longer than what we're running now. And there's really very little we can say right now.
So some people started looking at that. I mean, we can know what dynamical ejecta there is, and I think Mr. Ushibata's paper recently with Guanajo starting to look at other types of ejecta from winds too. So I think it's getting closer to the point where we can divide it into different parts of the ejecta, the winds, the dynamical ejecta, and so on. Of course, there is a question that some of the winds ejecta comes over a very long time scale that is beyond what we do in numerical relativity. But
right. Well, and there are accuracy issues as well. Yeah.
Yeah.
But yeah. So, Masar, are you going to talk about some of this stuff this week? Isn't it? A little bit. Okay. So yeah. So it certainly deserves more discussion. Okay. I think I'm done with that. Okay. So we just mentioned timescales. So there are lots of timescales involved here. In terms of remnant lifetime, just the merger and the in-spiral have a huge difference in timescales. Space, there are probably more here. These are just a few that kind of came to mind in terms of resolving things. And it's another thing with respect to last week, we talked about accuracy and how well things were going. I think we have when it comes to magnetic effects, we've got a big challenge in terms of resolving things. Things are just happening on a lot smaller scales than we're used to resolving here. These two, I think, we're probably doing pretty well. I think we're still, we've got some surface effects, and, we could still use more resolution. Okay, so I wanted to put this up again in response to last week talking about errors. So, I think there's been a lot of work with truncation error. It's not clear. I'm a little bit worried about coordinate gauge effects. I remember a paper vaguely that dealt with this many years ago. But since then, I haven't seen much discussion of this. And I think there's a lot of conformity in terms of most people are using BSSN. So when you compare codes that are doing BSSN, this is going to tend to go away. I mean, there's still some differences within this. Oh, I shouldn't use acronyms, but BSSN are just the acronyms of 4 people who developed a gauge, a scheme basically for which you can evolve gravity, general relativity. Okay, and then, so when it comes to the fluid, what we have outside the stars, so inside the stars we generally treat it as a fluid, ideal gas, or realistic equation of state, but outside the stars we have to have fluid as well, even though there may not be any fluid. And so what you have is a huge gradient at the stellar surface, and you've got to deal with that, but then also because of the way that relativistic fluid dynamics works, you have what's called this atmosphere. So you have density outside the stars. It's a factor of 10 to the minus 8 smaller, 10 to the minus, what do you guys have, 16 smaller? But the thing is the stellar densities are so huge, even that can be significant in sort of absolute terms outside the star. And in particular, you can get accretion onto the stars. It's completely artificial. When it comes to magnetic fields and the atmosphere, you get effects as well. So, I mean, in some ways you can look at this that we have it under control because you can vary the atmosphere. You can say it's 10 to the minus 16, it's 10 to the minus 15, and see what kind of effects, and you don't really see effects. And so that's good, but, depending on what you look at, it's not completely clear that things are completely resolved there. And then with the nuclear physics, I read these papers and you talk about errors of a few, errors of 50%, that kind of thing. And I don't have a good handle on that. Right? I'm used to solving partial differential equations where you look for convergence to a continuum solution. But when you read about this, that's not the issue. The issue isn't so much about solving PDEs. It's getting the physics right, which, of course, should be the goal. But I'd like to get a better handle on that. Okay, computational issues. This is just one slide. I just sort of want to mention some things. So hardware-wise, we're all dealing with multi-core. 10, 15 years ago, we were dealing with multi-node. So the first two are pretty well handled. GPU, I think Dave will mention some stuff. So we've done some stuff. I've got a nice scaling plot here. You can't read anything, which is perfect. Looks good, though. So what's going to, clock speeds aren't improving much. What's going to win out is not clear, and we're talking more and more investment of time and rewriting code and stuff like that. So, and no one wants to hear about this, but it's an issue that we have to deal with. There are different grid structures getting used. FMR, fixed mesh refinement. So you add, it's basically a non-uniform grid. AMR, you add grids where you need it and get rid of it when you don't. Otherwise, you could use what's called a cube sphere. So this is a two-dimensional kind of analog of what people are doing, and this lets you kind of resolve things better. Have you guys heard of this? I'm not sure how to say it. Does anyone know how to say it well? Voronoi? Yeah, so that's this. This looks pretty cool. So I've seen talks by Andrew McFadden, and it's not clear that this is going to work with GR and everything. But some of the results he's getting with this look really pretty cool in terms of resolving the instabilities. And then, so then I suppose this is basically some kind of finite element method, and there's discontinuous Galerkin, spectral methods, finite volume. So you can deal with it.
To help some of us in nuclear physics get a feel for the scale, what kind of machines do you run on? Are you running on Titan with lots of cores, or is it?
Well, so Stampede is what I run on. So usually hundreds of cores. We run AMR, so we run for months on hundreds of cores.
So nuclear physics has things like lattice QCD, where we're consuming a couple of billion core hours per year. So this is not at that scale?
Well, it's not at that scale, in part because they don't give us that time. Because I had a little logo from Exceed. They want scaling. They want their machines. All this stuff, and I keep putting in my proposal, look, we're doing physics, we're getting papers out. Why do you care what the performance is? But they are telling their reviewers to bug us about that. And in part because of manpower and stuff, just running this stuff. But so the AMR, it's very tough to get this kind of AMR to scale to thousands and thousands, or hundreds of thousands, of course. But we need lots of memory. Okay. Okay, this is basically my only slide about non-magnetic, non-neutrino BNS. And making this slide, I was a little surprised, at just all the work here. And some of this is not mentioned quite a bit. So in particular, this eccentric capture. So when you have kind of dense stellar populations, it's possible to capture into a binary. And so Franz Pretorius at Princeton, he's done at least a couple of papers on this. And this is also just recent, right? So I only go back to about 2012 here. Some of this has been mentioned last week. Actually, I guess most of this stuff here. So I wasn't going to say too much about this, in part because you don't see my name here. So, but I wanted to put it up in case people want to discuss or anything. But okay, so now I'm going to talk about electromagnetism. I'll talk sort of in general for a little bit, and then I'll talk about some of the work that I've done. Okay, so far from the stars, you don't have fluid, you have an electromagnetic field, and so it's basically electrovacuum. If you had fluid, they would evolve independently, so that would be no coupling. What sort of the field got started with is MHD, so ideal MHD, magnetohydrodynamics. So there you assume perfect conductivity, which is good inside the stars, at least pre-merger, before you lose superconductivity. You're not going to bite? Okay. So that's the standard lore, right? So I don't know if anyone wants to discuss that. So in general, basically, there's no electric field because in the frame of the fluid, because if there were, it would just move because it's perfectly conducting. The fluid is therefore tied to these magnetic field lines. The topology of the magnetic field essentially is fixed, at least in principle. And so then, again, in principle, there would be no magnetic reconnection. So,
just to clarify, perfect conductivity and superconductivity
different. Okay.
And so in a superconductor, depending on the scales over which you resolve the magnetic field, it could look very different. I mean, if it was type 1 or 2, flux tubes or complete flux expulsion. So the superconductor is going to try to constrain the field lines in ways that just ideal MHD probably doesn't know how to do. So.
Yeah, well, but from a practical point of view, 2 points, I think. When you look at the size of the so the grid size, the grid separation that we're talking about here, you're talking about very large scale, right? Mm. So you average onto that scale, and then you can get away with this kind of argument, I think, with one caveat, which is that you don't have quite the right stress energy tensor contribution. The energy contribution, the tension, and so on in the superconductor is quite different. Factors of maybe 1,000 different, depending on what your core field is. So that's important, but we don't have a good handle on how that should be described. That's the bottom line. There's not on the market a sort of plug and play thing that you could
put in.
Run. But that's so you can kick that back straight at us if you want. That's fair.
Okay.
But that's something people should be working on.
Something, not us, right? But at some point, someone should hand us over.
We would need to provide you with something. Right? That's the bottom line.
The field expulsion, that happens when it becomes superconductor, right? Once it's superconductor, if it's sort of born superconductor, then it's frozen in, right? The magnetic flux, I think.
Yes, I mean, it's frozen in flux cubes.
Right.
But there's still flux expulsion on some time scale. It's much, much longer than what you see here. But of course, then the question is, are the neutron stars that merge, are they old enough that you would have had flux expulsion from the core, yes or no? Because that would make a big difference for you. right? If you have
Oh, yeah.
the flux expelled from the entire core, more or less, right, and you just have the magnetic field concentrated in the sort of cross region, that makes a difference, right?
Yeah.
That's something you can actually test already. You can just assume that the field has some funny configuration, but it's not in the core. But
What kind of time scale do you need for that?
well, I think the answer to that question is you have to go back to 1969 and this famous paper by Bayman, Pettick, and it's the third person, right? Anyway, I think there's been very little work on this since then. And in fact, the details as to how they arrived at these timescales in that paper have never been clarified. They basically say it's an equation saying, here, oh, by the way, here's the timescale. We'll work this out. And we'll tell you the details somewhere else. We're still waiting. And some of these guys are getting old. So I think this paper, the follow-up paper needs to be written now.
So, but to go back to this point about the topology of the magnetic field and its location, I don't think this will lead to very large effects. I think the amount of energy, unless you are putting in 10 to the 16 Gauss in those old neutron stars, then that would be
No, it won't have any effect. So now I think you have to be very careful with what you're saying. The magnetic field will not have a huge effect on the gravitational dynamics.
Yes.
Right? But you made a bigger statement there. It will not have a huge effect. This can have a huge effect on electromagnetic possibilities, right? Because the amount of energy you can hold in the crust is vastly different from what you can hold in the core.
Well, so I was referring, of course, to the gravitational wave signal. But
Yes, I knew that, but I just had to have a go at you anyway, because it's Monday morning still.
Yeah, Niels, but this flux expulsion is only for type 1?
No, the flux tubes should be expelled on some timescale, yeah. Okay. But I think it's fair to say that unless, first of all, I think there's no obvious reason, and I work on these things, there's no obvious reason why I should believe this paper from 1969, because I haven't actually been able to work out where those numbers come from, apart from, make them up, right? And secondly, we don't have these models, so this is something someone needs to work out. And this is required for other problems as well. So it's not as if there's numerical relativity can't be held accountable for this not being possible, right?
Okay, right. But we should be aware that there is this extra physics that needs to come in at some point. Okay, so then there's this thing called force-free, which is getting pretty popular recently. And in particular, what happens is outside the stars, I mentioned there's an atmosphere, but pre-merger there's nothing there. There's no fluid there. But presumably there's magnetic field there. And so in particular, there's this regime of ideal MHD where the electromagnetic force, or inertia, or whatever you want to call it, overwhelms that of the fluid. And actually, I say there's nothing there, but there's what's called a magnetosphere. So it gets populated outside these neutron stars. I think I'll say something about that in the next slide. But in this regime, the density is very low, the pressure is very low. The magnetic field can be pretty significant. And in general, ideal MHD doesn't do very well with that, even though this is sort of some regime of ideal MHD. And so you can basically ignore the fluid except in that it provides charges and currents.
This is at what distance separation?
Well, this is outside the star, in the immediate vicinity of the stars.
When is that important?
Post-merger, well, it'll be, for electromagnetics, it'll be important from the beginning.
It's for isolated neutron star. It doesn't really matter. You have a rotating neutron star, you have a magnetosphere, you have these different regimes.
Right.
Now you put two of them together, it's always relevant, right?
Yeah.
Right.
All I'm asking, just like Luciano, is whether it's important for the gravitational.
No. Yeah, so I'll show you some evolutions.
Okay, but to pick up again on your question, magnetosphere is essentially a function of the spin rate of the star, okay? Because the magnetosphere ends with a light cylinder. If the stars are spinning very rapidly, these can be 100 kilometers. That's the time, the length scale at which these magnetospheres would start interacting. If the thing is not spinning very fast, then this could be much less.
100 kilometers means that it's important for
No,
for the energy, it's not.
Yeah.
It's important for the electromagnetic.
Just as an example, there are people working on on radio emission from interacting magnetospheres, for example. Could step in very, very early. But that's not the gravitational wave dynamics. But Steve.
Yeah, that's right. Last week we concluded that.
That's right. But Steve is talking about a much bigger picture here.
Yeah, yeah. I'm essentially ignoring the gravitational wave. I'll show you a nice little plot. But that's okay. So this force-free goes back. So I really like this slide because it goes back to there's a 66 paper too. It goes back even further. But in particular, so Julian and Goldreich say that basically outside the exterior of a spinning isolated neutron star, you're going to generate an electric field that's strong enough to rip charges off the surface and thereby populate this magnetosphere. Similarly, with a black hole exterior, the vacuum can break down. You get this cascade of a pair production that will populate the magnetosphere. So I always like to pause because I usually expect some kind of objection to this. But you guys are following, no problem. Okay, and so basically Spitkovsky kind of popularized this by applying it to a pulsar. So he took a sphere, literally just a sphere as a boundary condition, to model the pulsar, had force-free outside, let it spin with appropriate boundary conditions, and basically found this pointing flux that in some sense matched the pulsar. And then, this was followed up. I'm not sure about the 04 versus 06, but I'll have to look at that paper. Komisarov has done a lot with force-free, so maybe perhaps, I guess, Spitkovsky basically applied the force-free method to this. And then, so there's been a lot of work as well with the binary black holes, right? Because you can get electromagnetic signals from two black holes spinning around with this force-free method. And in particular, you get this collimated emission. So that was pretty exciting work. It's not terribly relevant to what we're doing here. But in terms of motivation, I think it's pretty good. And for anyone that wants to know more, Sam Garala and Ted Jacobson, I just put their big, long paper here. But there have been a few papers about this, not from a numerical perspective, but from a very kind of smart analytic method. And Jacobson, there's some lectures at Perimeter online where I've only looked at a few, but a whole series of lectures on force-free and some of these solutions that they find. Okay, so with that as motivation, I'll get to my work in a second. So just sort of some general talk here. You've got to control the divergence. So we used to have talks about this. This is mostly under control, though. Yeah, so one thing I should mention is that, so we have two regimes, at least two, theoretically three, right? We've got electrovacuum far away, we've got force-free right outside, and we've got ideal MHD inside the stars. And we want to get all those in there. And so somewhere I mentioned some matching methods. It must be on the next slide. But in particular, there's this thing called resistive magnetohydrodynamics. And in there, you get to specify the current. And so I'll say a few more words about that in a second. But just some physics issues that maybe we want to discuss this week. What's the right initial data for the magnetic field? Right now, we're just using seed fields, poloidal generally. So I don't know if anyone wants to say anything about that this week. What are the conductivities? So when you have a resistive approach, you can specify the conductivities. Basically like what we were talking about, what's going on inside the stars. Handling magnetic reconnection, that's going to be important for the work that I mentioned. In ideal MHD, you kind of get this sort of numerical reconnection, but in principle, it's not really there. And how to extract the signal, right? So, I'll show you some pointing flux, what we do with that to get light curves and more interesting kinds of stuff that observational astronomers can use. That would, of course, be better. Okay, so again, before I get to our work, so, in the olden days, a few years ago, we were doing ideal MHD everywhere. So a few different groups did this. So this is us. We use a code called HAD. There's the Illinois group. There's Whiskey. I'm not sure if that's everyone that's public. There's other works with MHD, but I'm not sure that there's others with just MHD and the binary neutron stars. I mentioned the matching regime. So here what you can do is you can try and match ideal MHD to the force-free. So we did sort of an explicit matching for a single neutron star, a collapsing neutron star. And then Shapiro's group, Vasilius at Zach, you were on this too, I think, with the black hole neutron star. So their scheme is more sophisticated. It seems to work pretty well. So that was pretty good. And then I mentioned this resistive MHD. So then Kiki and Carlos have some. And so, Carlos basically developed this, and then we used it for what I'm about to talk about.
So in terms of sophistication, there are codes that do combine magnetic thermal evolution in old neutron stars. Thinking about people like Jose Pons, who actually study magnetic field evolution in an isolated neutron star. They have terms like Hall drift in there. Is all that physics incorporated in these simulations?
So I'm not that familiar. I'm guessing no. In the resistive, there's some Hall effect in the conductivity.
Time scales are.
Yes, time scales. I'm going to say that. Time scales are very different. Time scale of heartbeat is, I think, should be thousands of years, something like that. So
time scales are very large because the temperatures are very small, and all these time scales are very rapid functions of temperature.
But there is an addendum, I think, to this, because in Jose's simulations, you're very near equilibrium, right? And the system sort of slowly evolves near equilibrium all the time. Right? Whereas here, in a merger, you can be far away from equilibrium. So it's not clear that these, but I think in principle, when you put in the resistivity, if you do it correctly, you've got the same physics in there, if you've got the composition as he has. Okay. But I think that this is a very recent work, if you go back just 2 years, right? So it's probably too early to say what exactly things mean. That's my feeling.
Okay, so now we're talking about some of my work with collaborators. So we took a binary neutron star. We evolved for just 2.5 orbits. I know that's going to make some people a little upset. But we get this, and then it merges, and we get that. That's a gravitational wave signal. Okay, but don't stare at it too much. That's not what we're emphasizing here. And so this is with the resistive code, right? And so we're looking for electromagnetic effects. And so basically we came to this from the supermassive binary black hole case. So the idea here is that we're in the LIGO band. A neutron star, unlike a black hole, can support its own magnetic field, so that you can sort of hope to get something a lot more interesting than what we got with the binary black hole.
What were the magnetic fields? I mean, do you have simulations with and without a magnetic field?
Sort of. I mean, you can think of this as without a magnetic field. But if you add magnetic field, this looks the same. So the energy of the magnetic field, it's not affecting anything. So we don't even show, it's identical. Yeah.
So typically in the binary black hole simulation, you see the John radiation and the chirp line thing.
Right.
You truncated things. So
yeah, I think so.
So how many orbits is typically?
Well, this is just 2.5 orbits. So 1, 2, 3, 4. Yeah. So I'm not sure exactly how much is cut.
I mean, the waveform doesn't start like in binary black hole, but you actually see it growing the chirp line, even if it's only 4 orbits and so on. Or I mean.
I suspect you're talking about something that would happen out here that's cut out. Yeah,
before, because I just don't see it in the papers. I mean, that usually I see this. I'm not saying only you.
Yeah.
But I would like to see in the binary black holes. We all show the burst of junk radiation and how it goes up. Is that the same thing that happens here, or is it?
Yeah, it is the same thing.
Okay.
It's the same.
Okay.
I mean, presumably it must, right? Because it's basically point particle out there, but. Okay, so we have a couple papers on this. So the first paper we considered this, so let me explain a little bit. So the U and the D, U is up. So, our binary up with respect to the orbital angular momentum. So we've got our stars going around like this, angular momentum's up, and we put on a dipole field. So UU is just 2 up dipole fields that go around here. So remember, they're interacting. There's a magnetosphere, right? So you've got these field lines and everything. And what I'm showing here is just the electromagnetic luminosity, ergs per second, the outgoing pointing flux on some sphere that encompasses the binary. And this is versus time in milliseconds. So here's basically where the stars touch. There's going to be deformation of the stars, so we don't really trust this regime terribly well. Because remember, we're doing this matching. So we need to sort of know where the star is and where isn't the star. And once they start merging, I mean, you know, you can always find a, quote, surface, but it's not a very well-defined surface. And so we found these luminosities, and so we find that the up-down case radiates about an order of magnitude greater than the up-up case. And then at the lower regime, this lowercase u, we took basically one star and essentially no magnetic field, a very small magnetic field. And so you get a very little luminosity. We look at some estimates, and in terms of the orbital frequency here, we match some gross, but I'm not going to talk about that.
What's the frequency of this radiation?
Well, this is pointing flux, so we don't have a frequency. I mean, presumably we could correlate it with the orbital frequency. But again, this is sort of extracting the electromagnetic. We're using the pointing flux as a proxy for that. But you're not going to see the pointing flux.
I mean, there's a lot of missing physics to process this into something you would see astronomically.
Right. Yeah.
But you would expect it to see in the X or gamma.
How sensitive do you think the results are to the matching?
In terms of if we used a different matching, or I wouldn't think that it's going to be that sensitive. I mean, in the sense that, you know, if we got the physics better, you know, I think sort of at the gross kind of coarse level, I think there's physics here.
How do you go from this to actually what we can observe? So the transfer function from pointing flux to, you mentioned this is missing. You know, is there a handle on what you would do from here?
I'm waiting for kind of the astrophysics community to tell me. You know, do we hand this off to some, you know, our data to some kind of post-processing that can evolve, you know, do the photon transport, generate light curves and spectra, and, you know, it's not clear.
But, you know, pulsars has the same problem. And
right,
they've had the same problem for 40 years. It's very, very difficult.
Yeah.
Sort it out before Sattva retires.
I'll write it down.
What does this luminosity depend on sensitivity? I mean, you have put up, down, up, and so on. But is there any property that you have put in magnetic phase?
So, yeah, they'll scale with the magnetic field squared. So this is something like 10 to the 11 Gauss. You know, you double that, and this goes up by a factor of 4. It depends on the frequency and the orbital separation, that kind of stuff.
And I guess the topology is because you have more recognition if you have this up-down configuration, right? How do you explain the difference up-down and up-up?
Yeah, so that's right. So, well, I'm going to show a similar plot for the next case. But yeah, so what's going on is the magnetic field gets deflected. The lines eventually get kind of stretched out, and eventually they reconnect. And that's going to liberate energy. And so basically what these are engines that transform orbital kinetic energy into pointing flux.
One would have expected this rise in luminosity, sudden jump, to depend quite critically, when that happens, to depend on whether it's up, down, up. It seems to be not so different. In one case it occurs slightly earlier, up, then up, down. So it's not too sensitive.
Why would you expect it to be very sensitive?
Mostly from the gravitational dynamics point of view, the hang-up is for longer if you have up than if it is up down.
But it is not. This is not
speed. No.
Yeah. Well, and dynamically, it's unimportant.
This
Gravitationally.
Is field, right? This is the field. Up, down, and up. It's similar.
No, the
from the
ungap
physics
doesn't-
point of view, the up is similar to up down.
Yeah, but
here.
but
the
the
fields-
spin there enters in the equations of motion. This doesn't enter at all in the equation of motion.
I think you said this the energy is coming from the orbital dynamics.
Yeah.
But then we'll
But-
expect some.
But it's tiny. It's
But
tiny.
it's
compared.
yeah.
So I think this is like magnetic fields riding on top of the gravitational binding energy, which drives through that hang-up. It's all the same in all the cases because it's
Right.
driven by the gravitational dynamics, and then you can sort of calculate this on top. So this has no back reaction effect at all. On that evolution is too small.
Right.
But
So
the
it can't-
magnetic field is assumed to be generated by the spin of the star.
No.
It's just put in. Yeah, it's just put in by hand.
So, how do the stars spin? Are they prograde spins?
Well, there's no it's irrotational.
Okay.
So then this luminosity depends on the conductivity, because if it's just coming from the connection, it should depend.
Oh, is that you mean in the in the magnetosphere?
Yeah, I mean,
Or-
you said that this is basically reconnection in the magnetosphere. So that depends on the resistivity directly, either numerical resistivity or the physical.
Right. No, yeah, but there's physical resistivity. Yeah, that makes sense.
So I guess this is what
Yeah, right. Yeah, I didn't. Yeah, I mean, okay. So I guess I'd have to modify. Yeah, so I suppose it would be, but we haven't looked at that.
Okay.
You know, we haven't looked at changing that. Yeah, so I would expect there would be changes, but I'm not sure qualitatively kind of how significant they would be. But it's an interesting question. Okay, so before I show the next slide, anyone want to guess what's going to happen if we take, so instead of up, up, or up, down, what we call now the aligned cases, what if I go like this, or like that, or like this?
The top curve actually suggests that something will die off very soon because it's pretty flat.
What do you mean, die out?
Meaning, like the magnetic field won't last until the merger, right? It will radiate itself away because it's pretty flat, isn't it? If you start the system, cells are.
I guess I don't follow why anything would die out. I mean, you continue to have the orbit, so you're essentially driving that engine continuously.
Clearly,
Yeah, but
much.
soon after the merger.
Yeah.
Oh, after the merger, yeah. I mean, we can't really trust this after the merger. I mean, plus there's going to be field amplification and stuff like that, and this is, you know, not like our highest resolution. Okay, so I'm about to show you. So these cases will remain. The scales, I think, are a little bit different. But so now we add in these other cases. So these three are just the same. So the dashed dotted lines are still there. So this is up, down, up, up, and u, little u. And then we add what's called p, so that's perpendicular. So that's, you know, we flip it like this. So pu, I'll ignore that for now. But p, capital U is this. P minus p is like that. And pp is like that. And you see that the time modulations are huge. But they're still essentially bracketed by those cases I showed before, you know, down here and this one up here. And so these are happening basically every half orbit. You get this kind of peak, and you could just imagine, you know. So when you have here, you've got the ability to reconnect. You know, so field lines from here basically come out, reconnect, and go through the next star and make these big loops. So this is a pretty tight configuration. And then if you kind of move it like this, you're stretching those field lines until eventually a half orbit later, then you can get reconnection. Okay. So whereas before you had it like this, and so you always kind of had this azimuthal symmetry, and now you've broken it with these cases.
So, Steve, should I consider the dot dashed green as the, you know, vanilla median? Statistically, if I have, because the distribution is going to be completely isotropic, should I take the dot dashed as the number I should keep in mind if I have to think about the luminosity?
You can. Whether you should,
because we don't. I mean, what we know is that they will come up with arbitrary spin directions. There is no reason to believe that they will come aligned or perpendicular.
Yeah, I don't. Is that true? I mean, I certainly. I mean, in the paper we say that sort of anything is feasible. I'm not sure that there's not like a more likely.
We don't have a lot of observation,
right?
But
yeah,
there
that's
is no reason to believe that there is a selection, out of the astronomical.
I mean, I would certainly imagine that the rapidly spinning neutron star is going to be aligned with the orbit.
Why?
Right? Well, because the way that you actually have something rapidly spinning, typically, if there's going to be a significant spin, right, is if you recycle it.
If you
recycle it, you've transferred mass, and if you transfer mass, it tends to align the system.
Again, there seems to be no indication that there is a spin here. So
right.
it's all supposed to have been non-spinning object. So what do you pick it up? Which one?
Yeah,
do you pick
this
up?
is not a spin. This is a magnetic dipole orientation, and the magnetic dipole can, we don't know exactly how that is produced.
Isn't there a reason to prefer the one with one large magnetic field and one small magnetic field?
Yeah, I think that is probably preferred. Which is basically going to be done here.
What's the magnitude of the magnetic field?
Well, we're using 10 to the 11 Gauss, but I mean you could scale it.
So that's small. Yeah.
Well, I mean, it's big to some people, but.
Instead of 10 to the 8, you're using 10 to the 11, but you're not using 10 to the 14.
Right.
So are you averaging the Poynting flux over some time scale, like fraction of a millisecond or something? How much should I trust these, P spike features? Clearly must be.
I think you should. I mean, for this simulation, I think you should trust it. In the sense of you start changing the resistivity or something like that, then maybe not so much. But I think this time dependence is there. I mean, for the assumptions of what we're running. Okay, so I mean, basically what I wanted to mention is that you can think of this as a circuit. These plots probably aren't going to be too helpful to you on this scale. But so that's the up-down case. This is the up-up case. This is the U little u case, which basically was considered by Donglai in this paper. So he's got this nice plot here. So here you assume basically a large magnetic field on one of the stars, and then this one's moving through that of the other, and it sets up this circuit where you have the current go through here and come back here. And so in the paper, we talk about some estimates, and we compare to what he finds. Here, what you can find, you can basically see some of these circuits. So the little arrows represent the current. So you've got a current that comes over here, and then it returns over here, and same thing on the top. And then, so this is the non-aligned case. I don't expect you to make a lot of sense of this. But the dynamics of these non-aligned cases were a lot more complicated than the aligned cases. I mean, in particular, I think it's this one. You've got field lines basically crossing the equatorial plane, which makes things a lot difficult. So it looks like these field lines are crossing themselves, which isn't going to happen, but you're projecting down onto the equatorial plane here. So just to sum up on the electromagnetics, and I'll try and cover the neutrinos relatively quickly. So, we've talked about some of the caveats here, but I think fundamentally what we're showing is that these interactions and reconnection can extract this orbital kinetic energy. I think that's a pretty robust effect here. The details, maybe we could argue over. But so we're getting luminosities of something like 10 to the 40th up to 10 to the 43rd ergs per second, and all that, of course, depends on what magnetic field these neutron stars come with. And then, so I just wanted to mention these, I've already mentioned the Lie paper, but, this goes back as far as 2000 with Hansen and Ludikov, who were estimating kind of what luminosities to expect. And so we're pretty much consistent with these. I didn't show it in our paper. We've got various plots that kind of study the patterns of the Poynting flux. And so the aligned cases were fairly collimated, whereas these more complicated ones, there are times where they look collimated, but then they're not. So if this is potentially observable, then perhaps it's even potentially distinguishable, that you could distinguish kind of what you're looking at. So that would be exciting.
Several milliseconds, like before merger, but potentially the radiation from post-merger is at least 5 to 6 orders of magnitude higher.
Right. Yeah, we're not studying the post-merger here.
Yeah. So what it means is that we can, the distance up to which we can see this might not be so optimistic, only because it's so much lower compared to the post-merger.
Well, but the times,
9, 10 to the 50, yeah.
You've got a lot of time to look for this.
A lot of
time. Okay. A lot of orbital cycles.
But presumably if you are in the very late orbit, right, your spin is basically not important. You haven't included it here because you're typically assuming that your spin period is much longer than the orbital period. But if you're going to extrapolate this over many, many orbital cycles, right, then the moment you go down to orbital periods of not 1 millisecond, but 10 milliseconds or longer, your spin periods are potentially commensurate, and so the picture may be very different, right? I would imagine that if your neutron star is spinning, the picture of the interaction with the magnetosphere is going to change significantly, right?
Yeah, I suppose that's possible, but presumably it's only going to increase the signal because you have more kinetic energy, essentially. These things are engines kind of spinning, so the spin is only going to add to it. And presumably we can model that as well, right? Once we've got spinning binaries, we can plug that in. Yeah.
Is there a rule of thumb for estimating this energy scale? U square over 8 pi over the orbital period?
Well, yeah, we've got some estimates based on the orbital frequency. I forget the details of it, but yeah.
And a question about the spin of the neutron stars. Is it realistic for the neutron stars to continue spinning slowly even after they start to interact tidally?
I would think so, yeah. Ilya's shaking his head yes.
I'm saying that I think it's good.
Yeah, I'm agreeing.
I agree with that.
No, but to produce co-rotation, that's what you're saying. You need viscosity, and the viscosity is too low to do this. In fact, they would have already been co-rotating if the viscosity was enough, given that they were orbiting each other for millions of years. So
that's because of the superfluidity.
Well, because all sorts of viscosities are too small to do this. Effectively, we don't know what is going to be the spin distribution.
Okay, so we're done with the electromagnetics? Okay, so, we started with polytropes, no shocks. Pressure is basically a function of density in kind of the simple form. Then we go to ideal fluid, ideal gas, in terms of a gamma law. So this has been pretty common. It's usually gamma equals 2 is chosen. I've heard some people say we should use higher gammas. So people complain about that. Piecewise polytrope, people complain about that. And then we get to realistic tabulated EOS. And guess what happened last week? People complained about that too.
Some people.
But so, we're happy to report some here. And, so all credit to the Kyoto, Tokyo, and Shibata who have been doing this for a long time. But so I'll talk about some work, I think. Well, in a second, I'll talk about some of the papers on that. Okay, so with this realistic equation of state, we're doing neutrino emission. We're doing it in the kind of the simplest way possible, which is a leakage scheme. So here, the role of these neutrinos, the reason why people want to include it is because of the post-merger. These neutrinos can remove energy. They can alter the composition of the remnant. They can, produce a neutrino wind that could be a power source for a gamma ray burst. Leakage is simple, it's popular, and it's arguably sufficient on the short time scales that we have here. There are more complicated methods, in particular some moment methods that Sekiguchi and collaborators have been using. So I don't know too much about that, but certainly that's much more advanced. It's sort of, people will complain, I suppose, until we get to this. This is not really feasible. at least the full treatment. But ultimately, that's where one would go. So the leakage scheme, I mentioned it's appropriate on kind of the short time scale. So it has kind of a long history. It's even longer than this, but this is what I put in here. So most of this is kind of the Newtonian or slightly modified Newtonian. And then with GR, 2010, Sekiguchi studied this. Evan O'Connor and Christian Ott did a 1D code shortly after that called GR1D, or at least now it's called GR1D. And that's a big basis for what we've done. We've kind of taken that and made it into 3D. And so the idea of this leakage scheme is that you take into account changes in lepton numbers, the electron fraction. You basically subtract out the energy of neutrinos that stream out of your simulation. We're ignoring momentum transfer, and we consider basically these nuclear processes. So this is kind of an old slide. I don't really want to talk about this right now. I'll talk a little bit about optical depth. So we made a few changes to some of what's done. I'll mention a little bit about the optical depth, and I'll show you these. So this is the emissivity, and this is basically the number, the emission in terms of a number density. Okay, so here's the slide that I wanted. So with respect to BNS mergers, so a couple, I'd say recent papers, but it's a few years old now. So they find high temperatures at the merger for the remnant, 50 to 70 MeV. They get a neutrino pair annihilation rate, and so what we're looking at are basically electron neutrinos, anti-electron neutrinos, and then sort of this catch-all for the heavier lepton neutrinos. So here's the moment method. I think there's a more recent one, maybe that I don't have here. But and then Francois, do I have? Yeah, here. Yeah, I had to put this in tinier font to get all the. I should have just used et al. But so they've been looking at the black hole neutron star merger. I'm going to mention the optical depth, and I noticed that you guys try out our way of both. So that was good. But so this is all, well, except for the Japanese group, there's been lots of work in just the past year or two. And then, Luciano, we've got with Filippo, the isolated neutron star stability. And so, we're looking at some of these, and I'll talk a little bit about some of the tests. Okay, so this is probably a little too detailed for this audience. I don't want to say too much, but one thing you need is the optical depth. And so what people have done is they've kind of, gone through different lengths to get this optical depth, and they interpolate to different grids, and they integrate rays to kind of see how hard is it for the neutrinos to get out. And you can look in different geometries and look over different numbers of rays and that kind of thing. And so when we were doing this seemed pretty difficult with respect to a parallel AMR where you've got grids scattered all over. It just seemed unnecessarily complicated. And so we were going to look at two different possibilities. One is to calculate the depth at any given point, you basically consider it a parallel circuit. So just like current basically has to find its way through, and you consider all paths, we could do that. Or even simpler, we just look at the neighbor. So you basically look at all your neighbors, and whatever their minimum depth is, that's yours plus some marginal amount just to get to that. So the parallel part didn't really work very well, but the minimum worked really well, and I'll show you why we think it works really well. So, when I was first talking about this, I've got this kind of justification because I assumed people would just think, that's way too simple. And then this paper came out basically as we were submitting ours, and this is very similar. And then, so Ian Hawke mentioned to me a year or two ago that the Eichenall equation basically is what we're solving here. So here, the optical depth is tau for some species I, and kappa is the opacity for that species. So if you look at the magnitude of the gradient of the optical depth, you should recover the opacity. So we're essentially integrating this equation. So instead of using this equation, I'll use it as a test. I'll just get my optical depth the way I've been doing it and calculate this and compare it to my opacity. And there you go. Right, so the magnitude of the gradient of the optical depth is in blue, and the red is my opacity. And so this is one neutron star, this is another. I just cut through my simulation at some time. Okay, so I feel like we're contributing two things here. One is this simple method that works great with parallel and with AMR, and the other is that this test seems to do a pretty good job of convincing you that this is good. Okay, so I just wanted to mention that. So let me just show you. Yeah.
If you go back, so what's the difference between, okay. You seem to be a bit more, with a larger variance. Do you do then any smoothing or?
No.
No, just keep it like that.
Yeah, this wasn't terribly high resolution. The post-processing was pretty quick and dirty. Yeah, I mean, if you look, and this is on a log scale, if you look at the stuff, it looks good. Yeah, here it looks kind of choppy. But I have movies later I can show you, and where they just look like plateaus. These two like mountains, like Mount Rainier's just moving around like this. It looks pretty good. Yeah, I didn't pay much attention to that, but yeah, I see what you're talking about. Right, yeah, well, I mean, on this scale, this is the same thing, right? Oh, this is the gradient. Yeah, so the gradient is kind of noisy, but I mean, it's still, there. Yeah. No. Yeah, the AMR grids would be outside the surface. Okay, so I put all this because in case someone asks me, and I always forget. So if you want to know anything, here you go, and then I'll show you. Oh, well, before I show you, some of the tests that we do. So we looked at isolated neutron stars. We compared the oscillation frequencies to Filippo's paper and some others. We do some convergence studies. This was a pretty strong test. So we were working with Evan O'Connor and compared directly to GR1D for certain neutron stars, and we're getting very similar types. Interesting, the most deviation we saw was at the surface of the stars. So that that's the surface of the stars is still an issue. And then sort of just qualitative agreement with some of the relative strengths in the different species of neutrinos with the black hole neutron star and other neutron star binaries. Okay, so here we plot the luminosity in ergs per second of the different species. So we've got the electron antineutrinos and the electron neutrinos in purple. And then the more massive neutrinos grouped together and called X. And so here's basically where the stars touch. So basically you don't expect any kind of luminosity here, but since it was basically a test, we left it on here. And then post-merger, the temperature increases a lot, and so you generate a lot of this emission here. And then so we can show different things. So here's the emissivity at different times. So all of this is, so I forget exactly when touch was, but I think this is just before touch, this is just after, and this is kind of long after.
I think you were making a comment before that you don't trust our simulations after the touch.
That was the electromagnetics.
Okay.
Well, it's more okay. Yeah, so
go back to the previous part, please. I just want to get to
okay, let me just clarify one thing. With the electromagnetics, we were using this resistive approach with the matching. And so once the stars start to deform, the matching in the surface, you can't really trust it. Here, there's no matching. Right. So this is just pure MHD. I mean, there's no magnetic field in this one.
So it's about 20 milliseconds, 30 milliseconds?
Well, so touch is, I think, like 14 something. And then we evolve for
35, 40 minutes.
Yeah, but we could have kept evolving and evolving. So this was a pretty long-lived remnant. I mean, eventually we just stopped. Right, and then I forget, I'm just going to look at what mass these were. So these are 1.49 baryonic mass.
So what's driving the neutrino luminosity before touch? I mean, is the temperature of the surface already so hot?
No, so this is effectively no emission So this is sort of a...
52 is no. Just keep that in mind. 52 is 0.
It's pretty sad when Niels is defending our work. I think that's scary.
It was irony.
Yeah. Yeah, I mean, so the usual thing is not to turn it on, and so then you literally have 0. Yeah, now, one thing that might...
You have some rates in your code that is producing this, and it's producing just, I'm guessing these are coming from the charge current reactions. Because the X neutrinos are hard to produce that way. You're getting a lot of the other stuff. And somewhere in your code, matter is hot.
The surface of your star is
Yeah.
by numerical error. There is numerical heating on the surface of the star, which is also where the optical depth is low, and where you don't have a very good measurement of why is the composition is not well computed either. So.
But what is the
my worry is that this is not negligible compared to the binding energy, gravitational binding energy of the star. So if you have numerical effects that are changing on that scale, then you would worry about what your gravitational waveform is.
But this doesn't feed back. Again, this doesn't feed back.
Well,
it's not the same way, though. I think.
I think it should be. I don't know what kind of resolution this is. It can go lower than that.
This is fairly well resolved. I think it's 300 or 400 meters.
I have more in mind than the 50 than the 51 as the floor for the emission before merger in our code.
Okay.
Somebody outside.
I think in our code, which is very similar, it's like 10 to the 50 to 10 to the 51 before merger, but different systems, so I don't know.
Yeah, let me just say one thing. So there was an issue with the initial data that didn't become apparent till like a month into running it, so we weren't going to restart it. And that's what's causing these oscillations, and I suspect that those oscillations may be essentially heating the surface more than in the best case. But even in the best case, you're going to get some kind of emission. Yeah, so but perhaps a bit lower. In terms of the feedback, I mean, in principle, there is feedback. We're leaking energy with these neutrinos. But again, it's going to be pretty small. If I totally turned off things, the dynamics, I believe, would be the same.
Yes, it's in many orders of magnitude below the gravitational wave.
I don't think it's the feedback that one is worried about. When you show a plot like that, if you say, hey, ignore 10 to the 52, but believe 10 to the 53, so are you saying that the error on 10 to the 53 per second is 10 to the 52, which is okay, it's 10%. Yeah, is that what you're saying?
Yeah, I'd be happy with 10%. Like I said, I'd be happy with 10. I'm not saying it is.
If it's 10 to the 53, then
it's about 10 to the 53.
That's pretty consistent with the other runs, 10 to the 53. So.
The error in leakage schema are a factor of a few. So.
Right. Yeah, and in their latest paper, they've got a nice description of a variety of errors. So I liked in that with the black hole neutrons.
How bright is the atmosphere these days?
Probably something like 10 to the minus 10. It's too big?
Sorry,
Yeah.
I don't actually remember what the maximum gravitational wave emission energy density is in these units. It has to be at least 10 to 55, right?
Yeah, it's a bit lower.
It's not
can go up to the 56.
Okay.
Even more. 10 to 58 is the absolute maximum.
Yeah, okay, but that's for a binary black hole
That's for
system.
binary black
Basically
holes.
at contact.
It can be a factor of, what is it?
But it should be a factor of our...
0.2 to the power of 10 small. So 2 to the 10. So yeah, it's about 10 to the minus 3 small. So 10 to the 56, 10 to the minus 3, yeah, 55. Still significantly larger compared to what we are seeing.
Okay, so I'm going to just show some quantities here. I'm almost done. Here's the optical depth, the electron optical depth. So you were talking about it looks pretty good. I mean, on this kind of scale, I suppose it's not too hard, but you can see basically in this contact region, the temperature gets pretty hot. And then we've got the remnant here. Oh, it's hot. The temperature is over here. But there's a big correlation between the temperature and the optical depth. What may be of interest, I'll talk about here. Here's electron composition, but let me just talk about this. Some of that mentions that. So in here what we have, the left half shows positive lepton emission, and on the right half it's the negative So you see that the antineutrinos are getting emitted kind of in this tidal region, relatively close to the remnant, whereas on the left side you're getting the electron emission, and that's pretty far from the remnant. And in particular, it's going to be colder out here. I got the temperature on the other slide. But so this was kind of our first go at this. So presumably things will get better. We'll get a better handle on the errors. Hopefully better understanding of kind of what physics needs to be extracted.
Sorry to say that it's going to be further away, but this is just a
What's that?
No, what I was thinking is that maybe they move away together.
Well, here the remnant is pretty central. I mean, here's the density here, so it's. Okay, so I've got movies I could show you. We're reaching a peak temperature of about 45 MeV. But let me just wrap it up. I think it's been okay. So here are just some things that we could, potentially discuss this week. We were talking about doing a long run from 20 orbits of the pre-merger without MHD, without neutrinos. Is that something that people want to do? Which EOS are we going to run? We talked about accuracy. For me, I'm sort of more interested in the new physics than the accuracy. I mean, obviously you don't want to do new physics with no accuracy. But, I guess, what struck me last week, all the discussion about accuracy, there's so much physics missing. It just wasn't clear in what sense we were talking about accuracy, and I guess that's why I've got the quotation marks after that. It'd be nice if people came up with new ideas for what to do with the atmosphere and the surface. Satya, I think you were asking about the Poynting flux and how to, get the real EM emission. I think, that's still an unsolved problem. And then nuclear physics. Anything anyone can tell me to help me with nuclear physics, I'd love. I've had people ask me about poly blocking. No idea. Landau levels, I had to go look that up. Is that important? What else am I going to be? Jim's smiling a bit, So I think these are going to be the weeks I'm not here. So if you could just wrap it up in a little, 5-minute PowerPoint and send it to me, that would be great. So I'll leave it here then.
So you want Jim's 30-second lecture on power blocking. That's perfect. Right, any questions? Kick off, Satya.
In defense of last week's comments about new physics, I think the point was not to focus on that at all, to focus on the part where new physics doesn't matter. Right?
Okay. Yeah, I didn't mean to attack it. Just,
So at least that was the last week's part of last week's effort. I think there are some aspects of it. We were also talking about post-merger, and there new physics does matter, I think. For what we were talking about last week, we should have good answers.
I think I would have a slightly different take on that. I'll go back and point at Sanjay and say, as a nuclear physicist, he would like you to promise, right, that by detecting these things, you're going to constrain one of the numbers he needs to understand the equation of state and physics, state of matters and so on at high density. Right? And the problem is when you put in the new physics, and if you say, well, look, we've got order of magnitude uncertainties of factors of this many, that just says that in post-merger evolutions, there's too much going on to make that promise. That's why we were talking about the pre-merger, pre-touch, tidal effects, when there's no such thing, where you could do this sort of idiot check as to whether your coding is as bad as Luciano's, and have those, maybe constrain those kinds of things, right? So that's why we were talking about that. Otherwise, I think, you basically summarized nicely how large the uncertainties are and the difficulties associated with implementing these things, right? And I think it would be very hard to put one extract on at this point.
Right.
And if you expect LIGO data in the next 30 years, then maybe you won't be there yet. More questions?
So you
show that the magnetic field orientation during the merger affect the electromagnetic signal characteristic, like you did all the orientations?
I very well. Sorry.
You showed one slide where the magnetic field orientation of the merging neutron stars and different characteristic of the signal, the electromagnetic signal.
Right. Yeah.
So when you change the configuration, is there something which remains invariant?
When I change what?
If you change the orientation like UU to UD and say UP, different configurations like two parallel, anti-parallel, and
Yeah, you get different signals.
So my question is that is there something which remains invariant, like some characteristic frequency, if you considering different conditions, different orientations of the magnetic field? And
Well, I suppose the modulations are roughly a half orbit. With any of these.
Okay.
So that's.
So that means if you take a Fourier transform of it, some of the frequency characteristic will remain centered at the same frequency.
I suppose, but I mean, first of all, we don't have a lot of data to do an FFT. Second of all, this isn't what's going to be, this isn't like a frequency that one's going to observe, right? I mean, you point a telescope at something like this, I mean, I guess ideally maybe you'd see this kind of modulation. But I don't think we'd need to do an FFT. We can just take the orbital frequency of the thing, divide by 2, and take the inverse, and we've got a frequency.
Have you checked whether the thing is that if you could see some kind of characteristic peak, and it's broadening or some, say, some overtone of it, then could you break some of these degeneracies, whether it is UD? That's what I was going to ask.
I don't know that you could break the degeneracy. I don't think so.
Okay, I was just wondering if you have computed the total radiated electromagnetic energy in this.
You mean integrate this over time?
Yes.
No. I mean, over what time would we? Yeah, it's a no him.
Do you have any idea of how observable that is in the EM spectrum? I mean, because you're seeing the inspiral.
Right.
Is it at that energy? I have no idea. Is that energy?
I think it's potentially observable. Is that fair?
I think Luciano put it very well. There's a lot of physics missing between the availability of power and how it will be converted into photons. That you cannot make any statement. All the microphysics. So you have to ask the question, how will this power be converted into photons? And then you have to do an analogous calculation about transfer to find out how those photons will get out. Until you do that, then I don't think it's fair to make any predictions.
Well, some people will just specify some efficiency, 90% of, multiply it, but.
But it would be spread out. I think the question is what band of the electromagnetic spectrum would you target? And I think it's
whether it will be collimated.
Right. Well, we have some information sort of on that. At least the Poynting flux. Now, it's going to have to couple through.
I think you put it again quite well in saying that, asking the question, is that your job to work that out, or are you expecting someone? No, a real, an X-ray astronomer or someone who actually more used to this maybe to do it. I mean, that's where, so that's a bit that's missing here, right? There's a building block that you don't have, and the simulators don't have, but that we need.
This is a recurring problem in many areas of astrophysics. The theoretical calculations go up to a point. Then there's this very dirty intermediate zone where you have to worry about interaction of photons with matter before you translate the problem into an observation. And it's always the toughest problem.
So we need the toughest characters. They're not going to be in this room, right?
Well, I mean, but
I think that was volunteering.
This is just making a comment that you could try the following game, right? You could say, let's imagine extremely optimistically, right? We're most sensitive in the optical, right? So let's just go ahead and imagine that somehow we're sufficiently fortunate that all of this power is in the optical, right?
You're answering a different question.
Yeah.
The question posed was, how do you make a prediction? The question you're answering, I think, is how does an observer who cannot rely on predictions go about tackling this problem? And that's exactly what you would do. You look under the lamppost.
Exactly.
Yeah, but if it's something you can be sure is that you're not going to see this in the optical. This is magnetic field generation. I mean, you might see it in the radio, in the X.
But you could do, if you do his calculation, you look at this energy available, and you can conclude if there's any point in investing that effort, right? That's the level we're at now. I think we're sort of saying, for this mechanism, there's no point in even thinking about it, or it's in the right level, right?
So what I was actually going to say, exactly. So what I was actually going to say is that these numbers, without having done this carefully, but these numbers look quite low to me. So my guess would be that actually I would be very pessimistic about your chances of detecting this, whatever band it happened to be processed in.
Yeah, I tend to agree. I mean, what we know from gamma ray bursts is that we can see them once we have located the gamma rays. And the luminosity we can see are 10 to the 48, 10 to the 50 per second.
I'm focused. That's the comment I made in the beginning. That this is so low that the distance up to which even if everything is converted to something like radio, it's very hard to observe. Unless it happens very close by.
So the robust conclusion is that if you're thinking about gravitational waves, all of this interaction between the magnetospheres doesn't matter. You can pump up the magnetic field even to 13 or 14, and this is not a perturbation. So if you have to take away some positive thing from this, through this exercise, you figured out that it's not going to impact the gravitational waves and spoil the interpretation of in-spiral signal.
On the subject of whether this is detectable, perhaps we should try to get on the same page, because I'm not sure I understand what you mean. It's the luminosity is very low. How far away do you want to be able to see?
Hundreds of megaparsec, or at least 100 megaparsec.
The luminosity of an accreting supermassive black hole is of this order. At low accretion rate, a mass of 10 to the 7 solar masses.
How far can you see?
So the X-ray power of a Seyfert galaxy is of that order. But that means that you have to arrange for all of this luminosity to come out in a relatively narrow band. You can't spread it over the entire spectrum.
And can it be?
You can see that to a redshift of 0.01, 0.05.
Yeah, generally, if it falls in another one, it can go
even further away. So
but Mike, this is exactly the problem. This doesn't outshine. There are many things that show this type of, especially if it is almost constant. Then how do you tell this is a binary neutron star rather than a Seyfert galaxy?
So we have to wait until there is a better prediction of the signature, because before you can make the statement, how would detect the
if there are and if there is variability in these peaks, then maybe you can use that. But then you have to have a very high localization, and before merger we're not going to see that.
But it is
to 100 degrees.
Because if Seyfert galaxy will have a variability over timescales of few months to years, and this is a transient event, as a merger, which you will see in few minutes and not before and after that.
Yeah. So if you have variability of 1 order of magnitude, yes.
Also, that's the other point. It's only for a few minutes.
Yeah, but
you
that's
put these two
a
neutron
problem.
stars.
That's for a few minutes, because how long is your exposure when you look at the Seyfert galaxy and you detect it at a redshift of 0.05, right?
That's true.
Right. Anyway, this guy, presumably what you did at that point.
All right, so we have one last question before we break for lunch.
So maybe just on your issue on atmospheres, I think there is suggestion how to do the atmosphere with this positivity preserving limiter. And, we haven't experimented with MHD and resistive MHD, but the hydro seems to work pretty well.
David's going to be talking about that, right? Yeah.
Yeah, I will talk about that. The main
Okay.
issue with positive preserving is it works very well if you are happy with ideal equational state. If you have nuclear equational state, yes, you can have the floor at 1 gram per cubic centimeter, but if you're going to use nuclear equation of state at that density. I don't know how reliable the thing is.
Yeah, but that's a different problem. That's not a numerical.
Can I just point out to you that was not a question, that was a comment. So I
Yeah,
still
no,
have
like
room
I said.
for the thought.
But the ease was a question.
Yes,
The
but
ease was a question.
yeah, but I've opened the floor for a question. That was a comment. So you have a yellow card, right?
I thought you already gave me several red cards.
No, it's like the World Cup, you know, all the yellow cards from last week are cancelled and you start again.
Oh, we have a final question or shall we stop? Okay, let's stop. Let's thank you. Oh, you can. Yeah,
How many yellow cards can you accumulate in this
I
before you
think,
get a red
just
card?
like in the World Cup, it depends on which team you play for. Sometimes you can kick someone and nothing happens. So if you're Brazilian, don't worry about yellow cards. Okay, let's thank Steve again.